Okay, so we talked a little about how weak bases could be added to water, so it can accept the proton, but the Kb here is very low, which means it's a very weak base, not a good base H ion acceptor. But it says how many moles of sodium benzoate are present in a 0.5 liter solution of a sodium C6H5COO salt solution if the pH is 9.04. So we have to first start off with our equation. So we're going to take this base, right? Which remember is a good, or bases tend to be H ion acceptors. So we got aqueous here, add it to water, right? And definitely at a unique equilibrium here. Not going to go to completion at all. And you get your, right, it's now going to accept the proton on this side in small amounts, plus the hydroxide ion, which makes it more basic. We're going to create an ice table here. Now see if there are any species up there that are not going to be a part of our ice chart. Okay, so you should have determined that H2O should definitely not be a part of the equation here, and here is your Kb expression then for this. So we have to use the information given that the pH is 9.04, but I'm interested in pOH, so I'm going to subtract 14 minus 9.04, and my pOH is going to be 4.96. Take the anti-log of the negative 4.96 pOH and let's get the OH concentration here, which in this case, when it approaches equilibrium, is 1.1 times 10 to the negative fifth molar for OH. So now that we know that, so in this case here, it's going to be a rare case, but here we're going to start off with 0 here, right? And that is the change. Small amount. Okay, to start off with, so the change here is that. Although we're not really interested in this part here, we're only interested in the OH, but we're going to put it anyway. Now, remember, initially we don't know how much sodium benzoate we started with, right? Because the sodium benzoate ion, remember, the Na here is just a spectator, so really we're trying to determine, they give us the amount of liters, we need to determine the concentration of it at equilibrium. From there we can determine how many moles because we have the amount of liters. So because the change here was 1.1 times 10 to the negative fifth, okay, at equilibrium then it's x minus 1.1 times 10 to the negative fifth molar. Okay, so now you can plug in all your values to all of these, and let's do this. And you also got the Kb up here as well, so do that now. Okay, you can now solve for x, but here no need of the quadratic formula. So when done correctly, x should equal 0.76 big M, which is the initial concentration we start off for sodium benzoate. So if you want to know then how many moles, if we know 0.76 is the initial concentration, then they're giving us the amount of liters, and now we could determine the moles up here, and the answer ends up being a roughly 0.38 moles of sodium benzoate. Must have been used, but again, Na is more of the spectator here. We were more interested in the benzoate ion.